Welcome to the deep dive. Today we're jumping straight into a really incredible story, Qantas Flight 32 back in November 2010.
Right. And our goal today is really to unpack how what seems like a tiny, almost insignificant manufacturing mistake led to this massive in-flight emergency over Southeast Asia.
Exactly. It's more than just, a story about a plane having problems.
Oh, absolutely. It's a fascinating look at how even really complex, rigorously tested systems can have hidden vulnerabilities. But also, it's about how the combination of design, crew expertise, and, safety protocols managed to prevent a total disaster.
Yeah, and we're digging into a detailed article that really breaks down the whole event, the causes. So the mission for this deep dive, trace that chain of events, understand the safety nets that actually worked, and figure out the big lessons learned from this near miss.
Okay, let's set the scene. It was November 4th, 2010. Qantas Flight 32, this massive Airbus A380, had just taken off from Singapore heading to Sydney. Only minutes after takeoff, climbing through about 7,000 feet, there was this sudden, huge explosion. Catastrophic failure of engine number 2, that's the inner one on the left wing.
We're not talking about just engine trouble, are we? The article describes the turbine disc basically just disintegrating, sending shrapnel everywhere.
Yeah, a really high energy failure. Bits of that exploding turbine just ripped right through the engine casing, tore into the wing structure, punctured a fuel tank.
Wow.
Even damaged the belly of the plane. And that first event just cascaded. It knocked out critical systems, flight controls, hydraulics, pneumatics, even some electrical systems.
It's honestly amazing the plane didn't just fall out of the sky right then. The force involved. Okay, let's back up. This was an Airbus A380, the giant double-decker.
That's the one. 4 engines, world's largest passenger jet at the time. Qantas was one of the first airlines flying them.
Right.
And this specific plane, VHOQA, they actually nicknamed it Nancy Bird Walton.
And the crew flying this enormous plane, they were seriously experienced, weren't they? The article really stresses that point.
Oh, incredibly so. You had 5 pilots in the cockpit that day. Captain Richard de Crespigny, huge experience, over 15,000 hours, plus First Officer Matt Hicks, Second Officer Mark Johnson, and then 2 check captains, Harry Wubbin and David Evans, who were also highly experienced.
5 pilots.
Yeah, the combined experience was just staggering. Something like 140 years in aviation, 71,000 flight hours between them. And believe me, that level of expertise was absolutely vital later on.
Okay, so let's get to the heart of it. This massive engine failure.
Yeah.
It wasn't some basic design flaw, was it? It was something tiny in the manufacturing.
Exactly right. The engine itself was a Rolls-Royce Trent 900. Now, basically, a jet engine sucks air in, squeezes it tighter and tighter through different compressor stages, low, intermediate, high pressure.
Okay.
Then you mix fuel, ignite it, hot gas spins turbines, and those turbines drive the compressors and the big fan at the front. Simple, right? Huh?
Simple maybe in concept. Yeah. So where did the manufacturing slip-up happen?
It was deep inside, in a part called the high-pressure intermediate pressure bearing hub assembly. Basically, this holds the bearings that let the turbine shafts spin. These bearings need oil, lots of pressurized oil, fed through a small pipe.
An oil pipe?
Yeah, an oil feed stub pipe. And part of this pipe passes through a little gap, a buffer space. The problem was right there, in that stub pipe.
What was wrong with it?
During manufacturing, they drill something called a counter bore, basically widening the inside diameter slightly, usually for a filter or something. But when they drilled this one, it seems the alignment was slightly off.
How far off?
Just enough that the wall on one side of the pipe ended up thinner than designed. We're talking about 0.5 millimeter too thin.
0.5 millimeter? That's tiny. How does that cause an explosion?
Well, think about the pressure. You've got high pressure oil constantly flowing through there cycle after cycle. After 677 flights, that thin spot just couldn't take it anymore. Metal fatigue. A crack formed and oil started leaking. This was less than 4 minutes after takeoff.
Okay, so oil leaking into where?
Into that buffer space, which is incredibly hot. So the oil instantly ignited. A fire starts inside the engine structure.
Right. Okay, here's where it gets really bad, I guess.
Yeah. This fire started burning against a seal. This seal is meant to keep the low pressure in the buffer space separate from the much higher pressure area behind one of the turbine discs. The heat damaged the seal. It failed, and high-pressure air rushed into the buffer space.
And that high-pressure air did what to the fire?
It turned it into a focused blowtorch. Like, literally, a super-hot jet of burning oil aimed right at the drive arm connecting the intermediate pressure turbine disc to its shaft.
And that drive arm just couldn't take the heat?
Nope. It was already under stress just from normal engine operation. The intense heat weakened it rapidly, and within seconds, it just snapped.
So the turbine disc was just loose.
Exactly, disconnected. But the hot gas from the combustion chamber was still blasting it, so it started spinning faster and faster, way beyond its limits, uncontrolled. 4 seconds. That's all it took. The centrifugal forces became immense, and the whole disc just disintegrated violently. This wasn't just a blade breaking off. This was the whole heavy disc letting go.
Which explains why the fragments had so much energy. The engine casing couldn't possibly hold that back.
No way. Casings are designed maybe for a single blade failure, but a whole disc burst is a different level of energy release. Fragments went everywhere. Through the casing, into the wing, down into the belly. One piece went down, others went up and sideways.
The article lists some really scary damage. Punctured fuel tank in the left wing, damage to the slats on the leading edge, the things that help with lift, right?
Yep, exactly.
And something like 650 wires severed. It's unbelievable. How does anything work after that?
Well, a lot of things didn't work properly. Those severed wires hit so many systems. Hydraulics, the green and yellow circuits were damaged, partial loss of electrical power, flight controls were degraded, ailerons, spoilers, the things you use to roll the plane. Autothrust went offline that manages engine power automatically. Braking capability was reduced, the pneumatic system had issues, fuel system problems, including losing the ability to dump fuel.
Which is crucial if you're overweight for landing.
Precisely. And they even lost fire protection for engines 1 and 2. It was just this massive cascading failure across the aircraft.
What was going on in the cockpit when this happened? The alarms must have been going crazy.
Oh, yeah. The first sign was a message on their main display system, the ECAM. It said, ENG2 turbine overheat. Almost instantly followed by just a flood of other alerts. The article mentions 35 messages in 20 seconds.
Whoa.
And the engine, even though it exploded, hadn't completely seized up. It was still turning. So Captain de Crespigny followed the ECAM procedure, pulled the power back on engine 2. That then triggered a brief ENG2 fire warning.
And they let air traffic control know straight away.
Yep. First Officer Hicks made a pan-pan call. That's the urgency call, just below a full mayday. They quickly figured out engine 2 was severely damaged, needed shutting down. But even the built-in fire extinguishers for that engine didn't work properly. Another problem to deal with.
So with all this damage, the sheer size of the A380, just keeping it flying must have been incredibly difficult.
It was a huge challenge. They had that continuous fuel leak, creating an imbalance. They were massively overweight, over 40 tons, too heavy for a normal landing.
And no way to dump fuel.
Right, the jettison system was out. Plus, they'd lost about 65% of their roll control because of the damaged wing systems. You really see how critical redundant systems are, but also how even they can be overwhelmed.
I remember reading that the cabin crew actually helped figure out the fuel leak.
They did. Passengers saw fuel streaming from the wing on the tail camera feed, the one shown on the in-flight entertainment screens.
Seriously, on the entertainment system.
Yeah. They told the cabin crew, who passed it straight to the pilots. That visual confirmation was really important.
So instead of trying to land immediately, they decided to hold. Why was that so critical?
They needed time. Badly. Time to work through all those dozens of ECAM messages to really understand what systems were working, what were degraded, what was gone completely. They thought maybe 30 minutes initially. It took nearly an hour.
Almost an hour just to figure out the state of the plane.
Exactly. Before they could even think about attempting a landing, overweight with damaged controls, they had to know what they were dealing with.
And even then, figuring out the landing itself was tricky, wasn't it? Something about the performance calculations.
Yeah, that was another big hurdle. The Airbus has sophisticated software to calculate landing distance needed based on weight, flaps, all sorts. But because so many different interconnected systems had failed in such an unusual combination, the software was basically spitting out garbage.
How?
It seems it was applying safety margins multiple times, incorrectly, because it couldn't make sense of all the conflicting failure data. It was actually Captain Evans who spotted this. He realized what was happening and manually put in their actual overweight landing weight.
Overriding the system.
Exactly. That forced the software to give a more realistic, though still very, very tight calculation for the runway they'd need. It really shows you still need that human expertise, even with automation.
And tight is right. The article said they calculated needing almost the entire runway, maybe 100 meters spare, on a 4,000-meter runway. That's cutting it fine.
Extremely fine, especially for an A380 that heavy, with compromised controls and braking. They requested fire trucks on standby, briefed the cabin crew for a possible overrun. The whole approach was tense, sluggish controls, manually managing speed with just engine 3.
Just one engine to control speed?
Effectively, yes. They even had to use the backup system just to get the landing gear down because the main hydraulics were damaged.
And then just before they touched down, a stall warning. Seriously.
Yep. They were right on the edge. Minimum safe speed to keep flying. But Captain de Crespigny nailed the landing. Incredibly smooth, apparently, on runway 2EC at Changi, almost 2 hours after the explosion. But it wasn't over yet.
Right, because landing heavy means problem stopping.
Big problems. The brakes on the left side landing gear got incredibly hot, leading to tires deflating. The fuel leak was still going, a huge fire risk on the ground. Then they lost all normal electrical power, couldn't start the APU, the auxiliary power unit.
So no power, leaking fuel. How did they even talk to anyone?
They had one working VHF radio left, just one, to coordinate with the fire crews.
And then there was that bizarre issue with engine number 1 still running.
Yeah, that was really strange and dangerous. The damage in the wing had somehow broken the fuel shutoff valves for engine 1, the outer left engine. The crew couldn't shut it down from the cockpit. Even the fire bottles for that engine were out.
So it just kept running.
For over 3 hours. The firefighters just had to keep pumping massive amounts of foam into the intake to eventually drown it out. Just shows how unpredictable the damage was.
And while all this is going on, 440 passengers are still inside. They had to decide whether to evacuate immediately.
A really tough call. Evacuating down emergency slides, especially from an A380's upper deck, carries a real risk of injuries. Lots of injuries, potentially.
Right.
Given the fire crews were there managing the immediate fire risk from the leak, they judged it safer to keep everyone on board and get stairs brought to the plane. Amazingly, with most comms down, they were using their personal cell phones to arrange this.
Using cell phones to get stairs to a stricken A380. Incredible.
It took about an hour, but they got everyone off safely. Not a single injury among the 440 passengers. Just remarkable risk management.
Meanwhile, back when the engine first exploded, bits of it were falling on Batam Island in Indonesia.
Yeah.
That must have caused panic.
Oh, definitely. A big chunk of the turbine disc actually went through the roof of a building. Caused a lot of damage, but incredibly, again, no one on the ground was hurt. There were initial reports of a Qantas crash, confusion everywhere. The Qantas CEO apparently found out something was wrong when the stock price suddenly dropped while the plane was still flying.
Wow. Okay, so everyone's safe. The investigation starts. They knew pretty quickly it was that oil pipe, but digging deeper revealed how that flaw got through in the first place, right?
Yes. The Australian Transport Safety Bureau, the ATSB, did a really deep dive. They confirmed the thin-walled pipe was the trigger. But their look into the Rolls-Royce manufacturing plant in Hucknall, UK, uncovered several issues.
Like what?
Well, one thing was how they defined datum points, the reference points for machining. They were slightly different between the design and the actual manufacturing process, which contributed to the pipe being machined incorrectly. Also, the acceptable tolerance, the sort of allowable error for that counterbore drilling was increased at some point, without a clear reason why. And there was evidence the whole hub assembly might have shifted slightly during machining, making that thin wall even thinner.
And the checks didn't catch it, the inspections.
The inspection methods weren't really set up to detect that specific kind of internal thinning effectively. One check measured the counterbore dimensions relative to a different point, not the wall thickness directly. Another might have caught it, but there were issues with how data was interpreted, and inspectors weren't fully aware of that datum point change. It shows how crucial it is that inspections directly target the potential failure modes.
The article also mentioned some flawed statistics and a retrospective concession. What was that about?
Yeah, that was another significant finding. Later on, when other thin-walled pipes were found, Rolls-Royce did a statistical analysis on some older parts to try and figure out the risk. But the analysis itself had flaws, not enough data, maybe misunderstanding the stats program. Despite that, someone in quality control essentially signed off on these non-conforming parts after the fact. That's the retrospective concession. They approved parts that didn't meet the original spec. And crucially, they did it without getting the required higher-level engineering approval, like from the chief engineer, a big procedural breakdown.
And the scary part was, after QF32, they found other engines flying with pipes that were even worse than the one that failed.
That's right. Several engines in service had pipes significantly thinner. It's highly likely they would have failed eventually too, maybe catastrophically. The investigation really pointed to a bit of a culture issue at that facility, some complacency, maybe not always sticking strictly to procedures.
But this whole event, thankfully, triggered major safety improvements.
Absolutely. Qantas grounded its A380s immediately for checks. EASA, the European Safety Agency, issued an urgent directive for inspections on all these Trent 900 engines. Rolls-Royce had to develop and install a new protection system, an IP turbine overspeed protection system, to prevent a disk burst if a similar failure happened again.
And the faulty parts.
All the original bearing hubs with those potentially thin pipes were removed from service and scrapped. Procedures between design and manufacturing were tightened up. Big efforts were made to improve the safety culture at Hucknall. And that whole retrospective concession thing was stopped, with much stricter rules for handling any parts that don't meet spec.
Even Airbus changed things.
Yeah, they updated the landing performance software to handle complex multiple failure scenarios more accurately. It was a system-wide response, really.
It really drives home that idea of layers of safety in aviation, doesn't it? The Swiss cheese model. Multiple things have to line up for disaster. Here, one layer failed spectacularly, but others held.
It's a perfect example. The A380's redundant design, like having multiple hydraulic systems, was crucial. But equally, you cannot overstate the crew's role. Their skill, training, calmness under immense pressure dealing with failure after failure. Just incredible. But it also shows how a tiny manufacturing flaw, that 0.5 millimeter, can have potentially catastrophic results. It highlights the need for absolute rigor and constant vigilance in aviation. And yet, the fact that nobody was hurt and that plane flew again after repairs is pretty amazing.
So wrapping this up, what's the biggest single takeaway from this whole Qantas 32 story?
For me, it's that a deviation you could barely see, less than 0.5 millimeter, started a chain reaction that led to one of the most serious in-flight emergencies imaginable. It's just such a stark reminder that in aviation, there's often very little room for error. The standards have to be meticulous, period.
But it's also, as you said, a story about resilience, isn't it? Resilience of the aircraft design, the incredible skill of the crew, and the industry's ability to learn and improve safety.
Absolutely. The fact that it ended safely, despite everything, shows that the layers of safety, while not infallible, generally work extremely well.
It does make you think, though. You wonder how many other potential near misses, maybe less dramatic but still significant, get caught by these layers without us ever hearing about them. And what does an event like this tell us about how much we rely on these super complex machines, and maybe even more importantly, on the people who design, build, fly, and maintain them? Definitely something to think about. If you are interested in digging deeper into aviation safety or accident investigations, there's a lot of great information out there. Thanks for joining us for this deep dive.